everyone. So, the geometry of information. Imagine holding the earth in the palms of your hands. Not just the physical globe, but also the planets, giant network information. Today, we live surrounded spherical data. Information is everywhere, and we love to think we know everything about happen on Earth. But the truth is we rarely see the full picture. Our sensor, for example, weather stations, ocean buoys, or telescopes pointing at the sky are scattered. And our observations are very limited. And this brings us today the next question. How can we extract, understand, and perfectly represent this continuous global data using only a limited and flawed set of measurements? To answer this, we need to dive into the math of the sphere. So think like a scientist observing nature. When we have data covering the planets, we need to describe it with a mathematical language. For that, we define waves. And the sphere has its own waves, and we call them spherical harmonics. Spherical harmonics is a fundamental language of the sphere. To describe the temperature of oceans or Earth's magnetic field, we need to add these waves together. By combining these waves, we define resolution. A resolution of world model. And we use more waves. The more waves we use, the more tiny details we can see, of course. But here is the problem, because we have mathematical limits on how many waves we can uniquely and reliably identify when we have a region, a specific region. So we define this observation subset of X. So imagine we have a function that lives on whole sphere. Let's say we have a distribution of gas in the sphere, in the atmosphere, sorry. And due to financial or practical delimitation, we can only measure it on X. And with that, so we have the next question. What is the sensor density I need inside this region X to reconstruct the original data when my view is so limited? And we have two approaches in data science. The first approach is the sampling. Sampling focuses on capturing the entire signal. It is about having enough information to reconstruct the original signal without losing crucial details. And we define for this the sampling set. The sampling set has a nature role. When you have, you need the sensor density of the sphere must reach a critical minimum threshold. We will see more later. The second approach is interpolation. Interpolation is like the perfect fit. If you want to find the functions that passes exactly through all the dates you have collected, for this we define interpolation set. And here the rule is the opposite of the sampling. If you want to fit data perfectly inside a specific region X, you cannot have an excessive density of data points. Now we define the critical density. So the critical density approaches the dimension of the sphere of the specific region X, divided the total sphere area. It provides the maximum information capacity of any region. When we are talking about interpolation or interpolation sets, the density must be lower than these quotients. And we are talking about sampling, the density must be higher than the same quotient. We have two sides of density. The first one study of our work tells us about the sampling set. So when to know avoid losing data, your lower spectral density must be 2 greater than the quotient, so the dimension, the area of the subset X divided the area of the total completed sphere. And the second study tells us to have interpolation to guarantee a unique solution. Your upper spectral density cannot exceed the same quotients. But what if we want both? What if you want the interpolation sets and sampling sets? Mathematically, that is exactly what we want. And we define the risk basis of spherical harmonics. The risk basis exists when the density matches the quotients we mentioned before. But there is a challenge here, the geometric challenge, because shapes matters. Not every X allows a perfect representation. And we have here a conjecture. So if we consider observation subset X has complex borders and cannot tile the sphere, the risk basis doesn't exist. What is the meaning of tiled sphere here? So for example, in the first picture, you can see the subset X like the spherical triangle. And in this case, this X tile the sphere. Why? Because you can stick multiplies of X together to cover the sphere and without any gaps. In the second picture, we have X like the spherical cup. This spherical cup doesn't tile the sphere, okay? Why this is important for us or for you, whether you are a physicist or biologist or telecommunications engineer? Because we have real-world implications. The first implication is when you scatter environmental sensor across the continent, let's say Africa in the first picture, this X has no symmetrical mathematical shape. So in this case, we need to accept redundancy. In the second case, the second example, we have data compression. So here there are geometric limits also to how much we can compress spatial data without losing critical information. And the last, there are analogous limits applied to quantum states, optics, and physical systems. Thereby, understanding when information breaks down allows us to design and create superior technologies. When the shape of the world or a piece of the world describes the rules, what we know about it perfectly, efficiently. So the geometry of the space is the geometry of the information. Thank you so much.